In this experiment, there was a system of a mass, a spring, and the earth. The purpose of this lab was to analyze the elliptical motion of the mass on the spring. So we looked at the motion in Tracker, and here it is, starting from right after the second that Dr. Greco releases the spring. And as you can see, each point, each center of mass is marked for each frame. The axis starts at the origin of the fixed attachment point, and the calibration stick is 0.7 meters long because that was the relaxed length of the spring when the mass was attached. So the first step to model this in Python was to calculate the Ks, the spring constant. So we know that the period is equal to 2 pi times the square root of m over Ks. So plugging in the values that we know, we find that Ks is equal to 6.869. The way that we knew that the period was equal to 1.52 was to look at the graph that was produced on Tracker and look at the amount of time it took for one cycle to be completed. So basically, the amount of time it took from this point to this point, and it was found to be 1.52. So after plugging in those numbers, we got the Ks value. The other initial values that we used were that the equilibrium length was 0.7, the relaxed length of the spring was 0.126, the mass of the spring was 0.402, and the time between frames was 1 over 10.5. So those numbers were all plugged into Python. Here's the ball's mass and the initial position vector found from the Tracker video. They were all plugged in. So then it is time to do the math. So we know that the change in energy is equal to the work done by the surroundings. We also know that the change in energy is equal to the sum of the energies, which is kinetic energy plus spring potential energy plus gravitational potential energy. So kinetic energy is equal to 1/2 mv squared, while spring potential energy is equal to 1/2 ks squared, and gravitational potential energy is equal to mass times gravity times height. So all of these values were plugged into Python. Here's the math for all of them: the gravitational potential energy, the kinetic energy, and the spring potential energy. And then we took those and found the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy. We know that the sum of these three values will give us the delta E. So here's that equation. And so then when we run the module, you can see that the orange ball, the model data, and the blue ball, what it's supposed to follow, are very accurate, which shows that the numbers I used are pretty accurate. Additionally, you can see from this graph that there's pretty high accuracy because the green is the model data from Tracker, and the red is the data produced by the computer. And so the two are pretty similar, which shows that there's a high level of accuracy. All right, so what does this all mean? So we took the x position and graphed it versus time to find the period for one cycle to be completed in the x direction. So to find this, we took the time between two crests, so this point, between this point and this point, and the period was found to be 1.52. The same procedure was done for the position in the y direction, and the same exact period was actually found. We took the distance from this point to this peak point and found a period of 1.52. So the fact that these two are the same shows a high level of accuracy because that means that that is the amount of time it takes for one period to be completed in both directions. So now the question becomes, what is the work done by the surroundings? And this is equal to 0. We know this is true because, as I already said, the work is equal to the change in energy. And the change in energy is equal to 0 because the energy is constantly converted between three forms of energy: the kinetic, the gravitational potential, and the spring potential. If the system didn't include the spring, the work would not be equal to 0. And you can see this on the graph produced by Python. Here, this blue line is equal to the change in energy, and clearly it's just a line straight through 0. So the final question is, what happens if we change the initial position? So if we change the initial position of the graph, then if we put it as 0.7 as the initial position for the spring, you can see that because the x direction didn't change at all, the motion in the x direction is the same, but the y direction values do change a greater amount. However, the change in energy is still equal to 0 because the path is still the same, but it's just a greater swing.